This tutorial will show you how to use the Cytoscape software to make some hypotheses regarding the function of an uncharacterized enzyme by viewing it within the context of a large group of related enzymes. We'll be using a sequence similarity network for the terpene cyclase-like 2 subgroup of the isoprenoid synthase type 1 superfamily, downloaded from the Structure Function Linkage Database, or SFLD. If you're not familiar with the SFLD, you might start by watching parts 1 and 2 of this tutorial series, which introduce the database. If you're not familiar with Cytoscape, you may want to watch part 3 of this tutorial series, which introduces the use of Cytoscape to visualize sequence similarity relationships. Here's an enzyme that's annotated in NCBI's GenBank database simply as a lyase. But if you look at the references, they're all large-scale sequencing papers, so the annotation doesn't seem to be based on experimental data. This sequence is a member of the terpene cyclase-like 2 subgroup of the isoprenoid synthase type 1 superfamily. So we're going to start by looking at a Cytoscape sequence similarity network for that subgroup and seeing how our sequence of interest fits in with the rest of the subgroup. Downloading the subgroup network from the SFLD, opening it in Cytoscape, laying it out, and coloring it according to Swissprot annotation was covered in part 3 of this tutorial series. So I'm going to start with the network just as we left off at the end of part 3. The first thing I want to do is to find our sequence of interest in the network. From the NCBI page, I know the NCBI GI number, and because that's one of the attributes in our network, I can search for that. There are a few different ways you can search these networks. I'm just going to show you one way to do it, using filters. I start by pressing the Select button at the top of the control panel. I'll create a new filter by clicking this upside-down triangle button, choosing Create New Filter, and then typing in a name. I'll call it GI because that's the attribute I'm interested in filtering by. And I'll click the OK button. I then click the plus button, choose Column Filter, which simply means I can filter by any of the columns in the table panel. Then I choose the particular column I want to filter by using this Choose Column list box. I'm going to scroll down to GI and select that. And then I can type my GI number of interest in this text box here. Cytoscape automatically performs the search. As you can see in the table panel, Cytoscape has found the sequence I'm looking for. It's also highlighted in the network in yellow, but it's a bit tough to see. Let's make it easier to see. I'm going to right-click on the node, select Edit, Bypass Style, Set Bypass to Selected Nodes. This brings up the Style Editor in the left panel, which you should be familiar with from part 3 of this tutorial series. Notice that this time, in addition to the default and mapping columns, we have a bypass column. I can use this to set the visual style for the node that is currently selected. I'll start by making it bigger by clicking on the size box in the bypass column and specifying a size of 150. Then clicking OK. I'll also set the fill color because the yellow color will go away as soon as the node is deselected. So I'm going to click in the bypass column next to fill color, and I'll choose cyan from the color picker and click OK. Now when I click anywhere else in the network to deselect the node, you can see that it's a cyan color. So that's where our sequence of interest is. My first question is, what is the closest experimentally characterized relative? It's kind of tough to tell by looking at the network here because our sequence of interest is part of this big jumble of sequences. So what I'm going to do is make a copy of the network and then filter it to a more stringent e-value cutoff. As the e-value cutoff is made more stringent, there are less connections between nodes that aren't closely related and we can hone in on the group our sequence of interest is most closely related to. I go to File, New, Network, Clone Current Network. As you can see, I now have 2 copies of the network. If I click the Network button in the Control Panel, you can also see the 2 copies of the network here. To filter this copy of my network to a more stringent e-value cutoff, I'm again going to use filters. I click on the Select button, and then the upside-down triangle, and choose Create New Filter. This time, I'm going to be filtering edges instead of nodes, and I'm going to be doing this according to their e-value. In the SFLD networks, rather than storing the e-value directly, we actually have the negative log of the e-value. So I'll call my filter minus log e, and then click OK. I'm going to click the plus button, again choose Column Filter, and this time I'm going to scroll past all the node attributes until I get to edge attributes, and then I'll choose minus log e. The e-value cutoff for the network that I originally downloaded was 1 times 10 to the minus 20th, which corresponds to a negative log 10 e-value of 20. So I'm going to select all edges with a negative log 10 e-value between 20 and 50 by typing those numbers into these boxes. Cytoscape automatically applies my filtering criteria to the network, and you can see that the selected edges have been highlighted in red. Down in the table panel, if I press the Edge Table button and then sort by the negative log 10 e-value attribute, you can see that the values for the selected edges range from 20 to 50, just as we would expect. So these are the edges that I want to get rid of. To do that, I go to Edit, Delete Selected Nodes and Edges. And now I want to lay the network out again. I'm going to use the same Y-Files organic layout that I used in part 3 of this series. So I go to Layout, Y-Files Layouts, Organic. As you can see, where before all the nodes were connected in a single cluster, we now have many discrete clusters. Here's our sequence of interest, clustered with some nodes from the SwissProt database, as I can see from the fact that they're larger and colored. I'm going to click on them to select them, and go to Node Table in the Table panel, and I can see that these are all epi-isoxazane synthases. So it looks like our sequence of interest might be an epi-isoxazane synthase or something similar. Of course, hypotheses that you make based on networks should always be examined in more depth. In this case, for example, we might want to look at our sequence of interest in the context of a multiple alignment with characterized epi-isoxazane synthases and look at how well it matches, particularly in the active site region. But because networks are so flexible, fast, and easy to work with, they're a great place to start for hypothesis generation. This concludes our brief tutorial on using sequence similarity networks to make hypotheses regarding the function of an uncharacterized enzyme, using sequence similarity networks downloaded from the SFLD.